Video berikut ini merupakan cara membuat gelombang berdiri pada tali. Jika kita memiliki sebuah tali yang diikatkan pada suatu tembok atau suatu benda yang keras, maka akan diperoleh suatu gelombang dengan cara menggerakkan tali naik turun. Pola gelombang tali yang dihasilkan akan memiliki bentuk sesuai dengan frekuensi naik turun tangan kita. Semakin cepat frekuensi yang kita berikan, maka pola gelombang tali akan semakin banyak. Perhatikan jika kita memberikan frekuensi pada gelombang tali dengan cara melemahkan pola naik ke atas tangan kita. Maka akan diperoleh suatu pola gelombang tali dengan satu perut saja. Kemudian jika kita menambah frekuensinya, maka akan bertambah pula pola perut gelombang tali. Jika kita mempercepat frekuensi yang kita berikan pada tali, maka pola perut pada gelombang tali akan semakin banyak. Gelombang tali pada dasarnya merupakan perpaduan dua buah gelombang akibat gelombang datang dan gelombang pantul. Berikut penjelasan tentang gelombang tali dalam bahasa Inggris.
Because one wavelength is always the wave going up, down, and then back. The length of one loop is always half a wavelength. So one loop is always half a wavelength. You shall find this very useful for standing wave problems. Now let's look at the natural or resonant frequencies in a string. Unlike a spring mass system or a simple pendulum that only has one period and therefore one frequency, a string can have an infinite number of resonant frequencies. A string can oscillate in 1, 2, 3, or any whole number of loops. The lowest resonant frequency has one loop, and it is called the fundamental frequency or first harmonic. 2 loops would be the second harmonic, 3 loops the third harmonic, 4 loops the fourth harmonic, etc. If we count the overtones, we only start after the fundamental frequency, so the second harmonic is the first overtone, the third harmonic is the second overtone, and then the third overtone. For the fundamental frequency, if the string's length is L, in the length L there is one loop, so L equals to the length of one loop. And the one loop is always half a wavelength. For the second harmonic, in the length L, there are 2 loops. And each loop is always half a wavelength. Since a loop is always half a wavelength. The length of a loop is always proportional to lambda because 1/2 is always a constant. In this case, the length of a loop is half that of the fundamental frequency. So the wavelength changes by a factor of 1/2 because the length of a loop changes by a factor of 1/2. And because the speed is frequency times lambda, we can compare these three numbers. For these two, first harmonic and the second harmonic, which of these three numbers do you think is the same? The speed, frequency, or wavelength? For the first and second harmonic, the speed is the one that is the same because it's the same medium. It's the same string under the same tension, so the speed is the same. That means if this one's wavelength is halved, that must mean the frequency has to be doubled because 2 times 1/2 equals to 1. So if wavelength is halved, the frequency must be doubled in order to keep the speed the same. That means the frequency for the second harmonic must be twice the fundamental frequency. If this one has a frequency, that's what we call the fundamental frequency. For the second overtone or the third harmonic, the length of one loop, again, it is half a wavelength, which means it's proportional to the wavelength. The length of one loop compared to the fundamental frequency is 1/3 of that. So the length of one loop changes by a factor of 1/3. That means wavelength changes by a factor of 1/3. Because speed equals to frequency times lambda, just like before, the speed is the same. That means if the wavelength changes by a factor of 1/3, the frequency must triple. So the third harmonic must have a frequency that is 3 times the fundamental frequency.